let's talk about Chapter 7, linear regression. Now, what is linear regression? Well, this name kind of says it all. We are going to fit a line to data. And to know how to do this, we have to know what kind of data we're using. We are going to use two quantitative variables. That'd be a variable like height and weight. Now remember that height is going to be the explanatory variable in this example because it's on the x-axis. Y is going to be the response, and by the response we mean what we're talking about, i.e. the variable of interest. And then when we do linear regression, we are going to write an equation. Now here's a big thing, and jumping a little bit forward, you might have heard the famous equation, y equals mx plus b. Yes, we are kind of doing that, but we, preferably in statistics, say y hat for the predicted y equals b0, which is the value of y when x is equal to 0, plus b1, which is the coefficient of the first x in the model, x. Sometimes we put the 1 here. A lot of times when we only have one x, we no longer put the 1 next to it because it's just the x variable in the model. This is still the same idea you've seen if you've done algebra, where you have right here the mx right here, and this is going to be the b. So it's just a reordering right there of the y hat equals b0 plus b1x, as we've seen before with the y equals mx plus b. And preferably, I like the b0 because it's when x is equal to 0, y is expected to equal to b0. And I like the b1 because you can talk about for each 1 unit increase in x, we expect y to increase by b1 units. More on that coming up here shortly. We talk about how to find this. So we are creating what is called the line of best fit. What do we mean by a best fitting line? Well, you can make a lot of lines. There's a line, there's a line, there's a line, there's a line, there's a line. But what it turns out is one of those lines fits the best to the data. And by best fit, we mathematically do this. The mathematics, we don't go into too much detail here. Look for more advanced classes like BAS 320 here at the University of Tennessee on this. We reduce the sums of the squared error. Error is the distance, how far you are away from points. Now, here's the thing. If you just find all the error, how far things are away, some are above, some are below. And if you were to average that error, it would average out to the line. But if you mathematically did it with some positive, some negative, you average them, what quantity would you get? You'd get 0. So that is why instead of just finding the sum of the squared error and summing it up or averaging it out, we go and we square it. And by squaring numbers, if they're negative, like if that's below the line, it becomes positive. Not the best square right there, that's more like a rectangle. You'd actually more square it and find the square of the error and find the sum of the squared error to figure out how far are these points away from the line in a mathematical sense. And in some instances, the line does really, really well. This one does pretty good. But sometimes we get a line like this, where all the points are directly on the line. And that's amazing. It might mean we did too well and something's weird with our data. Like, why does our data look this good? And that would have no sums of squared error, which is topics we're going to be talking about through this lecture. If you remember from correlation, we have scatter plots are the relationship between two quantitative variables. So it's a bivariate quantitative display of data is a scatter plot. With scatter plots, we can look at the strength, direction, form, unusual features. Direction is merely positive or negative. Form, I like to talk about linear or not linear, and there's many types of nonlinear forms. Strength is how tight the points are around the form. So although this is parabolic or nonlinear, we could say it's super strong. This linear one right here I'm drawing next is weaker because if you draw the form, the points are tighter around the parabola there, and they're more scattered around the line. Unusual features, there's a lot of unusual features to think about, but the one we usually focus on right here is going to be outliers, which are things that go against the bivariate trend. Notice how all of these are ideas with scatter plots. An unusual feature can differ if we're talking about univariate data with histograms. Unusual features, one of them with scatter plots, would be things that go against the bivariate trend in the data. And if you're wondering why I keep saying bivariate, because in the X sense, this is not that unusual right here. It's Not even that unusual in the y sense. So if you think about on the terms of x, it's actually towards the mean of the x because the center of the x is right there for the data. It's kind of close to the mean of the y, but in the bivariate sense, it escapes what we would say is the density ellipse. It's kind of further out away from the relationship, and it's kind of odd in its xy combination, making it a bivariate outlier. The two variable combination is an unusual combination. We need to know when we are going to be doing regression, and it goes back to the conditions of correlation. Quantitative variables. That literally means you have something like height and weight. I like to call this QQ for two quantitative variables. Straight enough. That means your data is decently straight. You might see a little bit of a bend there at the end. It can be kind of weird, not too weird, decently straight. You can always fit a line to data, but is it straight enough? That one's straight enough, I would say. But if you have data that looks something like this right here, that's not straight enough. If you have data that forms a parabola, that's not straight enough. And be careful, because I've had students say to me, well, you can still fit a line. Yeah, you can, but you shouldn't. It's not straight enough. No outliers is going to be the condition we talked about previously, or the idea of unusual features. When it comes to no outliers, you do not want outliers because they can drastically impact correlation, and regression is basically built on top of correlation. It's kind of an extended topic of the idea. So why do we dislike outliers? Because they can dictate the correlation or the regression, and then we're not really talking about the data in a holistic sense. We're just talking about the outlier that is causing the line to go down. Here is the line without the outlier, and here is the line with the outlier. Notice how it drastically impacts that. That's why we say QQ, straight enough, no outliers. We don't want those if we're going to talk about a true linear relationship or something that is well described by a linear relationship. Here's a data from the Burger King menu items with the protein explaining why there's so much fat. And there's some more weird issues with this that we'll kind of get into. Kind of want an even scatter of the points. We call that homoscedasticity, but this has a bit of what we would say is heteroscedasticity. And those are some fun advanced words right there. Hetero meaning different and homo meaning same. It shows some heteroscedastic, but here's the thing for right now, it's pretty straight enough. It's pretty straight enough. Are there extreme outliers? Not so much. Some of them are kind of deviating. Light outliers, I'd say, and it's definitely two quantitative variables. QQ, you got it. Straight enough, really great there. No outliers, pretty good. Notice how the conditions aren't always like, we win, we're perfect. The only ones we can say for certain we're good on are QQ, because you have to have two quantitative variables. That's not a kind of a iffy thing. You either have two quantitative variables or you don't. And straight enough is kind of like, is it good enough? Yes, it is. And then no outliers is also kind of like, those don't look too bad to me. So remember the conditions, remember how to check them by looking at the plot. So here we are with the regression that we've talked about, and this is the equation that solves mathematically. For the previous equation, we are going to be predicting fat over here, and that's what y hat means, is the predicted value of y. X is merely what we see in the equation, and then B0 is the expected or predicted value of y when x is equal to 0. You can show this mathematically right here. If you simply plug in a 0 and reduce the equation, well, when x is equal to 0, that's the predicted value of y. And also right here, if we start increasing x by 1, then y would increase by b1 units, and that's what the b1 stands for. For each 1 unit increase in x, we expect y to increase by b1 units. We'll say those more slowly coming up here in a moment when we focus in on some interpretations, which my students have to write out or type out for the test. So here is the equation for the graphic you saw previously. This equation right here, and let's drop it in there. This equation is the equation for this right here. So there is the graphic, and there is the equation for the line you see on the screen right there. There is the equation for it. And think about what this means right here. As long as we drew our line pretty decently, because we're adding it right here, a lot of statistical software will do this for you. We can think about right here is the 8.4-ish, and then we would go and try to go through the data, and that looks pretty good right there. Think about what these correspond to. This 8.4 is the value, and actually I made a small error because the y-intercept is actually going to be here. Graphic, a little bit extension. So that means, because I thought I did pretty well with my drawing, we need to draw the line to be hitting about here at 8.4 and go through the data at the slope, which is kind of hard to know, but it would go through the data. And we have now drawn the line, and let's point out what we have. The 8.4 is when x is equal to 0. That's why I was putting it right there and then starting the line through the data. Might not be perfect, but the 0.91 is for each 1 unit increase. So it'd be little tiny increases in here. For each 1 unit increase in protein, we expect fat to increase by 0.91 grams on average. We expect, not that it will, it's the expected. A lot of things differ by that. Sometimes we increase. Notice how there's this decrease right here. Like if you compared this one to this one, you would expect the one to the right to be higher, because as more in this one right here I'm talking about, you'd expect it to be higher. It doesn't. Not everything follows the pattern with linear regression. Just a model of what we expect given the data we see. So we know what these quantities are. Make sure to write underneath them predicted value of y equals the intercept plus the slope times the x variable. When you have this right here, you can solve for many things. You could say, well, you know, my menu item has 10 grams of protein. So with this, you would go in here and solve this out. Luckily, 10 is a nice number to multiply by. You'd go and multiply by 10 and get 9.1, and then simply add this right here to get the predicted fat, which is not the actual fat. The predicted fat is going to be equal to, doing math here on the spot, 17.5. So the predicted fat right there is equal to 17.5. But with that prediction that we just made of 17.5, we're not always correct. So the predicted value of 17.5 would go over here as the predicted y hat. Maybe we look at the menu item and it actually has 15 grams of fat. That is what we call the observed. And the observed, visually speaking, is wherever the dot is. So take a look right here. That is the observed fat for this, because that's where it hits on the y-axis. Its prediction is down here where the line is. Everything on the line is a y hat. So all of these right here are y hats. And if you trace over from one of them, you can see their value of y by just seeing where it hits the axis. A residual is how far away the observed is from the predicted. Huge note right there. A residual is how far away the observed is from the predicted. And what's really great is when you have residuals, above the line is a positive residual because things were higher than they were predicted to be. And below the line is a negative residual because things were lower than they were predicted to be. And on the line perfectly is a residual of 0. So if it's perfectly on the line, there is no difference between what we observe and what the model predicted. So think this over for a moment. If the menu item actually has 15 grams of fat, then what would the residual be? What would the residual be? If it actually has 15 grams of fat, we can say the observed is what it actually is. I like to call it the actual minus the predicted for RAP. So residual equals actual minus predicted. What would the residual be? And the residual would be negative 2.5. That means we predicted 17.5. Let's go grab our model right here and erase some stuff. We predicted 17.5, which means we're over here, about here on the model. It's 17.5 prediction. And it actually has 15 grams of fat, so it's down here. And notice the residual shows us that it is 2.5 below the model. And this is not meant to be a point, that is meant to be just the prediction from the model. So the green dot I put right there is the y hat, and then the actual is the blue dot. So actual minus predicted, sorry about that, actual minus predicted, and that is equal to the residual right there. So there is the equation. The yellow line right there, which is about 2.5 below, it's going down negative, shows us that the actual was 2.5 below what we predicted to be the grams of fat via the model. And another example right here, just showing the steps, and you can go through and solve the equation to do this by plugging in the value of x right here and getting the predicted value of y hat, and then looking at this. So if you look at this right here, if we go actual minus predicted, remember residual, E equals actual minus predicted, and that's the notation. Residual is E, y is the actual value of y, and y hat is the predicted value from the regression equation. We go here and we solve out. we say 22 minus 36.6, and that once again is going to be negative. And this is confirmed if you look at it visually right here, because the point is below the line. So since it is below the prediction, the residual is going to be negative 14.6. Make sure to put the negative right there because it is below what it was predicted to be. And if we calculate all residuals and add them up, we mentioned this previously and we can show it with a smaller example. If we have a line of best fit, the points might go around it like this. This one might be +2 above, this one might be -2 below, this one might be +1 above, and then what would the last one be? Mathematically, it would have to be a certain thing. This one's 2 above, this one's 2 below, the last two +1, what would the last one be? It would be -1, because all the residuals sum up to 0, they average out to the line. A lot of models aren't as fun and as perfect as this one and easy to show, but if you were to sum up all the residuals for any model, they would even out and flatten out to the line right there because the line is the average of all the points. So with this right here, we want to come up with an equation and then use this to model reality. And we have the two quantities, which are the slope and the intercept. So the slope is going to have a specific interpretation, as is the intercept. Let's start with the slope. The slope, which is noted as B1, can be said for each 1 unit increase in x, we expect y to increase by B1. Now notice, you need to put in the words right there. For each 1 unit increase in x, for each 1 gram increase in protein, we would expect fat to increase by B1 units, to increase by an additional 0.91 grams of fat. And you can throw the on average on there. Some people are really stickler for on average, but if you say we expect or predict on average, those things are what you need to say. You don't want to say will, because that makes it sound like cause and effect in your interpretation. So let's not look at the interpretation, let's try it by memory right here. We've got, for every additional gram of protein we see in a Burger King menu item, we would expect that the fat would increase by 0.91 grams on average. So make sure to notice what goes where. This is B1, which goes right here. We have the context of the x variable right here, and we have the y variable interest over here. Make sure to place them in the proper order. Write down, for each 1 unit increase in x, we expect y to increase or decrease by B1 on average. The increase or decrease is dependent on the sign of the slope. The slope is positive, increase. The slope is negative, decrease. Now for the intercept is going to be the expected or predicted value of y when x is equal to 0. So when x is equal to 0, we expect y to equal B0 on average. And notice how when you say when x is equal to 0, we expect y to equal B0 on average. Let's highlight the things in here. When x is equal to 0, that'll always be the same, but we have to input x right there. When x is equal to 0, we would expect or estimate, those are good words right there, for y, here it is right here, to equal B0. Remember where these quantities are located in the regression equation with y hat equals B0 plus B1x right there. We'll just highlight those also below the equation. These are great things to write down in practice and know what the notation is. Knowing the notation is a huge help for being able to solve these. So think about this. When x is equal to 0, we expect y to equal B0 on average. For each 1 unit increase in x, we expect y to increase or decrease by B1 units. Notice how the B1 is paired with the each 1 unit increase. So we have right here, on average, each 1 unit increase. So for every, and I like to say 1 unit increase, so for each additional 1 unit increase, we would expect that it would increase by B1 units. And right here, the zeros are paired right here with this being the quantity of B0. So very important to notice the B0 goes with when x is equal to 0. And for each 1 unit increase in x goes with B1. Good way to memorize those things right here. When we are doing this, we might want to think about what is the x and the y, or how do we interpret these things and what is the context of them. So if we have We are trying to understand average home game attendance each year and numbers of wins a team has. Well, the intercept for this model might be B0 equals negative 200. So if you have a negative intercept, does it make sense? Well, when number of wins for our team is equal to 0, that's possible. And you could get 0 wins, it'd be a pretty bad team for baseball. It's a lot of games to lose. We expect the average home attendance to be negative 200. That is not logical. A key note to know is sometimes your intercepts are meaningless, and you'd want to state this. So it's a little addendum we add to the interpretation, like when our wins each year are equal to 0, when we have 0 wins in a year, we expect home attendance to equal to negative 200 on average. This is illogical because you cannot have negative home attendance. So sometimes the value of B0 is illogical due to the scope of the data, the possible range of values. But you could have other things right here, like when somebody has a height of 0, we predict their weight is equal to 80 pounds on average. That's the value of B0. Remember, when x is equal to 0, so when x, I'm just making up these B0 numbers to give some interpretation. When x is equal to 0, we expect y to equal B0 on average. So when someone's height is equal to 0, we expect their weight to equal 80 pounds on average. Why is that illogical? You can't have a height of 0. When someone's height is equal to 0, so I'd say this is illogical because you can't have a height of 0. Make sure to write those things, make sure the reader understands it, and knows that sometimes when you interpret these, the intercept can be meaningless. The two reasons the intercept is meaningless is either because your value of B0 is impossible for y, or setting x equal to 0. In this example is impossible. You can't have a height equal to 0. So that is impossible. When we find the least squares line right here, we do a little bit of mathematics. Now, I post a solver for my students to help them solve this, and it just plugs the numbers in. Because we focus more on the interpretations than the solving of mathematics. So let's see the equations. And once again, you can use solvers or other things for this. Let's focus what the notation means. This is how the slope is found. The slope, which is known as B1, is going to be the sample correlation, that's the value of sample correlation, times the ratio of the standard deviation of the y variable over the standard deviation of the x variable, specifically sample standard deviation because it's lowercase s, not a sigma. So knowing the notation, especially for our classes, is going to be way more important than solving this by hand because that's just plug the numbers in and solve it, but not a bad formula to solve. The next equation right here, which is for the intercept, is going to use the slope coefficient that we just found, but it's going to times it by the mean of the x variable. So that's the sample slope, B1 is the sample slope, times the sample mean of the variable x, and we are going to subtract out of y from this. So the sample mean of variable y minus the slope coefficient times the sample mean of variable x. And this is what is equal to the intercept coefficient of our model. Coefficient just means number. The value we found for the intercept. When we say coefficient, just means a number. And so once again, an important thing to write down here in your notebooks is going to be what these things mean. B0 is the coefficient estimate of the intercept. B1 is the coefficient estimate of the slope. Y bar is the sample mean of variable y. X bar is the sample mean of variable x. If you're using JUMP or any other statistical software, you can go to Analyze Fit Y by X. Analyze Fit Y by X has you put in the explanatory variable there, and we say maybe protein explains why there is so much fat in a burger, and we can hit OK and get the analysis. We'll go more into this analysis here in a moment, but you can see a lot of really great analysis with the R squared and other quantities there. But I do want to point out, and it might be hard to see, the regression equation can be found there. We'll zoom more on it a little bit here. And also the estimates can be found down here in your output by going to fit line. Once you fit the line, you get the equation up there, and you also get the estimates down there. So what I've highlighted in purple is going to be where your estimates are, and it's just going to write out the equation y hat equals b0 plus b1x with the estimate of the intercept and the estimate of the slope. There is this last condition we haven't talked about. 2Q straight enough, no outliers, and regression has one more. The last one is plot does not thicken. Once again, this is a little bit subjective because when is it thickening too much? Well, here is a plot that is perfect. Thickening is when it expands or contracts around a line. So here's the line through the data. And here is a plot that has a lot of thickening and thinning. Thinning a word? Maybe. So it starts out thicker, gets thinner, gets thicker. This is bad because it is not the same variance around the line. Sometimes this is called equal variance. Sometimes it's called homoscedasticity versus heteroscedasticity. And so the one you want is going to be the graphic on the left that stays about the same thickness throughout and about the same because that one's perfect. It doesn't have to be perfect. It just has to be good enough. Or do you want the one that just goes crazy, starts spreading out, or goes back in? Do you want to stay the same thickness or be a much wider, different thickness throughout? You want this one over here, one that stays about the same thickness. And the reason is because if you think back to correlation, correlation is how tight the points are around the line. So if we're going to describe this relationship has the same sort of idea throughout it. So when we come up with summary statistics like correlation, it has the same correlation throughout. So it's not going to be ill-described in certain areas by a correlation value. This one is weak down there, stronger here. So talking about it as one big idea is not a good thing because it has many different ideas inside of it. We want a model that explains all the data, not in different ways, but in the same way throughout. So once again, the data on the left passes the plot does not thicken. You want to say that plot does not thicken. Good. The data on the right fails the condition, and these are the extremes. A lot of them will be iffy, and we'll look at some examples. You want one that kind of does well. We talked about explanatory and response variables, and once again, the explanatory is going to be your X variable, and the response is what you talk about. Think about if you have a response, you'd be asking why is something going on, and someone would tell you that. There's not always clear examples of explanatory and response, but there are some here. Think about this. If you are going to figure out, like you're trying to buy a home, what would you want to talk about? Well, you could talk about square footage. You'd probably be more interested in talking about the selling price. And you'd probably say that the square footage of a home explains why something is a certain selling price. Also, if you think about kind of antecedent and consequent, then you could think about something like college GPA and SAT score. SAT score comes from high school, so maybe your SAT score would explain why you have a certain college GPA. And always explain it that way, like, I want to talk about, people's college GPAs. Maybe their SAT scores explain it. Sometimes people also call the Y the dependent variable. Not a fan of those words because it's a little mathy, and the X is the independent variable. That comes from the equation on how values of X solve for values of Y. Like, the value of Y depends on what X is. And so that's more mathematical than statistical lingo we talk about, where we say, like, what is the explanatory variable? What is the Y variable of interest, the response variable that we're going to talk about? So here's a mortgage example, going through looking at the percent or rate of mortgages. And let's go right here and take a look in billions of dollars in interest rates. Oh my gosh. 14.7% interest. That is going to be very hard to pay off. Let me put it that way. And if you notice, we kind of see something here. We see this increasing as the data goes down, and we see this decreasing. So that's kind of a negative relationship because one is going up and one is going down, negatively correlated. And we can think about what kind of line would fit through this data. And we can think if it has a little bit of a nonlinear form, which it kind of does. There's a little bit of a bend to the data. Not a strong one. Is it straight enough? I'd say decent. I'd say decent. It's probably straight enough. Some statisticians might get mad about it, but I'm going to say decent. Is it two quantitative variables? Definitely. Are there no outliers? Pretty good on the no outliers. And the plot stays about the same thickness. This is a pretty good one. Is it a reasonable reflection of reality? I'd say so. So now we can get some of the quantities, especially correlation right here. The correlation between this, we already knew it was negative. And notice how the matrix is symmetric. So you could grab either value because you're just pairwise correlating those, the X and the Y variable. And the correlation is negative 0.84, which is a very strong negative correlation. And it looks mostly linear. And it is statistically significant because the p-value is below 0.05. So we'd say that this correlation we see here is very unlikely by random chance. And yeah, line looks pretty good. So what is B0 and what is B1? Take a moment, look at the equation down below. That is the jump output. I said we'd look at it a little bit more. And where is B0? Where is B1? Well, B0 is right here, And it's actually off the screen. It'd go further up and hit about there because this doesn't quite go to 0. And then the B1 right there is going to be this value right here, which is for each 1 unit increase in billions of dollars, how much it goes down. So for each 1 unit increase in interest rate, we expect the mortgage rate to go down by decrease by $7.775 billion on average. And when the mortgage rate is 0, we expect the interest rate to equal, when the interest rate is 0, we expect the mortgage in billions of dollars to be 220.893. Here's the thing, though. Is that meaningless? It is. No one's ever going to give you a 0 interest rate. If you ever hear that there's a 0 interest rate loan, you should take all the money you can, put it in the bank, make interest, and pay that back whenever you have to. Because 0 interest means there's no interest that you have to pay. Not the way the world works. So it's pretty meaningless because there's no 0 interest loans. That's, here, have this money for 10 years and then just hand it back to me. As I said, just put it in the bank. So it's pretty meaningless. And so we've done some interpretations right here. We interpreted the slope, we interpreted the intercept, but let's look a tiny bit more about those residuals right here and get into one of our last big concepts. This concept right here is going to deal with where is the variation coming from. So when we look at the variation right here, we're thinking about r squared. Now, r squared is not correlation. R squared is not correlation. It is derived from it. It is a different idea. R ranges from -1 to 1 and shows us or helps us understand the strength of the linear relationship between two quantitative variables. R squared, because we're squaring it, it can no longer be negative, ranges from 0 to 1 and tells us the percent of variation explained in a y variable from the variation in an x variable. Notice I didn't even say two quantitative variables because we can do sums of squares reductions for other types of relationships. And it's not technically derived from r then. In this instance, we're deriving from r, squaring it. But the idea of r squared can be used for other relationships where we can do box plots and find out variation from a global mean. Those are other topics for another day. But the big idea right here that you have to know is r squared is not r. So don't interpret it like correlation. We'll go into some interpretations here in a moment, but do not think that r squared is correlation. It is not. What we're looking at right here is how much variation we explain. This is what is left in the residuals. This is the variation from the mean of y. Now notice the variation from the mean of y would look the following way. We'd have data like this, and we'd input the mean. In more advanced classes, we call this the naive model. And the variation would be calculated the same way with a sum of a squared error. And so when you think about this right here, there's error from the mean, but over here on this one, and we'll make it color-coded correctly, so you can kind of tell which models I'm talking about. Here is the original variation, and then here is from the mean, or excuse me, the line, and you notice it's smaller. In that model, the rainbow model right there, the points are much closer and there's less error, smaller residuals. And that would be, in the rainbow model, the observed from the prediction, which is the line. The naive model is the observed from the mean of y. That's more complicated than we really go. What we need to know is going to be that r squared is variation explained, variation accounted for. So how well does our model do at reducing this sums of squared error, which is the original variation that exists from the naive, which is the mean of the y variable? Well, we can just look at it. R squared right here. Once again, derived from r. Take r, right here, the correlation value, and square it. Now that we have r squared, it's 58 or 0.58. We multiply it by 100. It's a number contained between 0 and 1, and it's the percent of variation y explained by the variation in x. And from this, we would say that 58% of the variation in fat is explained by the variation in protein. Let me write this out right here. Blank percent of the variation in y is explained by the variation in X. This is huge right here. Blank percent of the variation in Y is explained by the variation in X. X, right there. Y is right here. R squared, R squared, right here. Plug in the numbers, times by 100. 58% of the variation in fat is explained by the variation in protein. 58% of the variation in fat is explained by the variation in protein. If you've been following along this lecture, please try saying them out loud. Please try writing them down. Knowing how to interpret these things only works if you practice and you say them too. So the lowest R squared we mentioned is 0. An R squared of 0, one of the most classic relationships, is going to be something like this, where the line is flat. And think about it. That's the same as the naive model, and the line doesn't explain anything. An R squared of 1 is going to be a perfect relationship, which was when we have all the dots directly on the line, and the line would explain all the variation. So R squared, once again, tells us how well we're doing, which if we get an R squared of 1, we did exceedingly well. And we can look at this to see if it is statistically significant coming up here in a moment. So now take a look at this right here. This is the mortgage in billions of dollars explained by interest rate. How would you interpret it? Try to write it out. Try to say it out loud. We have right here the R squared, times it by 100. 70.5% of the variation in mortgage in billions of dollars is explained by the variation in interest rate. Remember, it was a lot tighter of a relationship, so the line did a pretty decent job. This is what the 70% variation explained looks like, 70.5. And this is the one that only had, let's go back to the BK menu one, only about 58% of the variation. And look, it's more spread out. The tighter the points are around the line, doesn't matter if it goes up or down, the tighter the points are, the higher the R squared. But one thing we want to know is how bad do we do in totality? To do this, we need to look at the residual plot. A residual plot is a plot of all your residuals. To simply make a residual plot, take your original data that looked like this, make the line flat, you have a residual plot. I want you to think about why this is the case. We'll look at the original data. Here we are with the original data right here. Better graphic. And if you want to make it into a residual plot, take the data, make the line flat. And that is technically a residual plot. We can enhance it a little bit more by redoing the axis. Think about this. If something is directly on the line, what would its residual be? If something is directly on the line, what would its residual be? This is a bit of a review question. If something is directly on the line, it would have a residual of 0. Let's rewrite this axis right here, where something is directly on the line has a residual of 0, and that we could then space it out properly and look at the residuals in totality. So look at what I've done to this graphic here by making the line flat, setting the line equal to 0, and if you look at the graphic that shows the residual plot for it that is created, here it comes, 3, 2, 1, pretty much the same plot. Sometimes it spaces out differently, but depending on how it stretches and stuff. But once again, you just take the line, make it flat. Anything on the line would now have a residual of 0. If you set it equal to 0 because it's perfectly predicted. Anything above would have a positive residual, and anything below has a negative residual. Just make the line flat, whether it went up or down. And this can help us better examine, and here's a huge thing, a residual plot is the best way to check the fourth condition of does the plot thicken. A residual plot is the best way to check that fourth condition of does the plot thicken. And I'd say, yeah, that's got some problems right there on plot thickening. Take a look at this residual plot. It's a residual plot. Notice how it says residuals. And is there plot thickening? Oh, yeah, there's plot thickening. That's a bit of a problem right there on the plot thickening of the data right there, taking it from another aspect. And truthfully, we didn't originally notice this with the data until we put it in a residual plot, and we see there's a bit of an issue. Is that really horrible? It looks pretty bad. I'd mention that in my report if I'm writing it. It'd be a major concern. So when you are doing this right here, we need to mention one last big idea. And this is the idea of statistical significance. Statistical significance is when your p-value is less than 0.05. What does it mean? Well, it depends on the test. You always know that what you saw was unlikely by random chance. For this test, on the slope, the null hypothesis, which is what we assume, is that there is no slope, or slope equal to 0. You could write it that beta 1 is equal to 0 in statistical notation. So if you're wondering for the stat notation, it is that beta 1 right there, the true coefficient of the slope, is equal to 0. The alternative would be that the true coefficient of the slope is not equal to 0. So the alternative is basically that there is a slope, which would be an alternative of beta 1 not equal to 0. So if you wrote out the alternative hypothesis right here. Now, if our data were to look in the following fashion, if our data looked like this right here, what do you think the p-value would be? If our data looked like this, do you think there's evidence of a slope here or evidence of not a slope? If our data looks like that, you'd be like, that looks something likely given there's no slope, which would mean high p-value. P-value equal to something like 0.89. You're like, that looks super likely given there's no slope. I'd say that looks very unlikely. If there's no slope to the data, we shouldn't see that. And so in other words, the p-value here is probably going to be basically close to 0. It can't actually get to 0, but it can be very, very close, like 50 zeros, and then a number after that. So it's going to be virtually 0, and thus we would reject the null hypothesis and say that we have evidence of a slope. So let's look at one of the jump outputs for this and see what it looks like in output to do an example right here. So here we are with a spinner example. You take a spinner, you flick one, you flick the other, and they stop on something, and then you look at the relationship. Ooh, that kind of looks like a slope to me. The slope value is negative 0.317. That kind of looks like a slope. I don't know, I better go to the statistical test on this. Now remember, we are looking on the statistical test for a p-value less than 0.05 when we test the slope. This is a test of the slope. You have to know what test you are doing to know what the results mean. And looking at the statistical test, we see a p-value that is above 0.05. I knew it was right there. And with this, we would not reject the null, which means we do not have evidence of a slope. So once again, in the test of a slope, a low p-value is evidence of slope. The evidence of slope. Let's write that right there. And a high p-value is no evidence. We do not have sufficient evidence, not sufficient evidence. So we do not, in this instance, we do not have sufficient evidence of a relationship between the two variables, that there is some sort of XY slope relationship. And that does it. Let me know if you have any questions. Good luck.